Hello class and welcome to week 3 according to my calculations. So in this week we will address a couple of topics from chapter 14, which is called the name of the chapter is Advanced MOS Topics, and then one section from chapter 15, which is Memory Circuits. So first day of this week I will do the advanced MOS stuff, and then the second I will do memory circuits. And again, for each of these we'll have one recording for theory, one recording for examples and problems. Okay, all right. So this topic, again, this is the table of contents or topics for this week's activity. Chapter 14, we have 1, 2, 3, of which most of the focus will be on 2. I may mention a little bit on 1 and 3. And then next class we'll do just topic 1, which is 15.1 from the chapter on memory circuits. Okay. All right. So this is kind of a continuation of what we have done so far with CMOS and MOS in general. We've learned a lot about MOS and CMOS. We've seen a lot of advantages to CMOS, but we've also seen that there are a few problems with CMOS also. So more techniques to be able to use MOS technology, but some tricks and some special circuit approaches to help overcome some of the problems of MOS and CMOS so that we are able to do more with cheaper. That's the goal of some of the ideas of this chapter. So standard CMOS logic, the advantages, right? It's easy to design, has the maximum possible voltage swing, is robust, more noise immune, dissipates no static power, that's a big advantage, and can be designed to provide equal high to low and low to high propagation delays, right? The T, PHL and PLH, those can be designed to be pretty equal. So all these are advantages of CMOS. Now the disadvantages of standard CMOS is that it needs 2 transistors for each additional gate input. For gates with high fan-in, this makes the chip area very large. It increases the total capacitance, increases the propagation delay, and the dynamic power dissipation. While there's no static power dissipation, but the dynamic power dissipation, which happens when you're switching, that can also be pretty large. So these are some of the issues with CMOS logic. So there are some approaches and some technologies which have been tried in the past, and they help overcome at least a few other problems with CMOS. So the first of these, 14.1, is something called pseudo NMOS logic circuits. So I'm not going to spend too much time. This is a big topic, but we at NAU have not included the details of this as part of the requirements. The next topic will be covered in more detail, but I thought I would at least bring one slide to tell you what pseudo NMOS is in case you run into this sometime in the future. So we know this is a standard CMOS inverter on the left side here, and this is a pseudo CMOS inverter. So what you'll see is this PMOS transistor, which is part of the pair, right? They always come together. But this CMOS transistor has been connected in a different way. Its gate is grounded. Now, if you look down here, you'll see that For a 4 input NOR gate, for example, right? Normally, with a standard approach to this gate, you would have 4 NMOS transistors on the bottom for the pull down network, and you would also have 4 PMOS transistors on the top to create the PUN, the pull up network, right? But what you'll notice is the entire pull up network has been replaced with just one QP, which is a PMOS transistor with the grounded gate, right? Same thing with the NAND gate, right? Also, you have 4 inputs A, B, C, D for the NAND, and what I'm showing here is only the bottom portion, the pull down network. The pull up network, which also would have had 4 in parallel, 4 PMOSs, has now been replaced with just one PMOS. So the bottom line is a lot of chip and silicon area can be eliminated by using the pseudo CMOS inverter, because the entire pull up network is gone and all you have is one PMOS transistor. So by replacing the pull up network of a CMOS logic gate by a single permanently on, the way this is connected, it will always be in saturation and always be on. Considerable savings in transistor count and silicon area can be achieved. Pseudo NMOS is particularly suited for application in which the output remains high most of the time. So if there are certain applications where you know that 75% of the time the output is just going to be high, like for example in this OR ABCD, right? We know that always one of them will definitely be high. Then we know that the output remains high most of the time. In such applications, the static, or the opposite, I guess, all 4 of them, none of them will ever be on, so the output is always high. Then such applications, pseudo NMOS, actually this is pseudo NMOS, not CMOS. That's what I should write. Okay, so in such applications where the output remains high most of the time, the static power dissipation can be reasonably low, since the gate dissipates static power only in the low output stage, right? So this gate only dissipates power in the low output stage, and we never get to low output. Most of the time we are high, so power is saved. Further, the output transitions that matter would only be high to low, because the gates are always, the output is always high, so occasionally you have high to low, where a short propagation delay is possible, right? So for these advantages, the pseudo NMOS approach is pretty useful, and I will leave it at that. Let's move on to the next most important topic for us, which is something called pass transistor logic. So pass transistor logic, or PTL, on slide 6, utilizes MOS transistors as voltage controlled switches in the series path from input to output. So pass transistor logic, compared to CMOS logic, uses fewer transistors, runs faster, requires less power. So PTL is frequently used together with standard CMOS logic to implement some special functions more efficiently. Okay, so instead of always relying on CMOS all the time, certain applications where you require just switches to be used, to be made available between the input and the output, then it's possible to use what is called pass transistor logic, or PTL. So here are some examples, right? So Y is A and B and C, right? It's logic and gate here. Y is A and B and C. So this B and C can be created or switched using MOS devices. You don't have to rely on CMOS for this, right? And having this little y equals ABC function within a complicated circuit, if such is the situation, then you can use this pass transistor logic. Similarly, if you have to implement y is equal to a into b plus c, you can see it's pretty simple, right? Now, to implement either of these, y equals abc or y equals a into b plus c, if you look at the standard CMOS approach with inverters, you can see that you'll probably have 8 to 10 um, devices, MOS devices, both NMOS and PMOS, to do the same thing, right? If you go back to your chapter 13 notes, you'll see how complex it can be. And this can be even more complex. And then you need a PUN and a PDN and all that stuff. But here we are saying that you can pull off something like this with just a couple of MOS transistors. Okay? So that's the idea behind PTL. Now you may have other things to do in your big circuit, but for this particular job of implementing something specific such as this or a simple or a simple logic function, you can use PTL and save a lot of hassle. Okay, so each of these switches can be implemented either by a single NMOS transistor like shown here, or by a pair of complementary MOS transistors connected in CMOS transmission gate configuration. So I keep telling you that we can do this with single transistors, but another improvement is if you are allowed to use two transistors. So you're back to CMOS again because you have a NMOS and a PMOS. But even here, it's much easier to design in this way, thinking of these as switches rather than thinking of them as inverter pairs. Okay? And so as we go through this, you will understand why this seems even still better compared to going with full, CMOS inverter approaches. All right. So what you have to remember then is you can have a switch either with a single transistor or with a pair of transistors, and if you have a pair of them of opposite polarity, then we call that a CMOS transmission gate configuration. Okay, I have a couple of slides here that maybe is confusing, so I'm just going to skip those, maybe take it out. But let's move on to the next slide, which is slide 10. So before we proceed too far ahead, there is one note here, an essential design requirement. This is section 14.2.1, which says that in the design of PTL circuits, every circuit node must always have a low resistance path either to VDD or to ground. So in this case, there is no definite path where you can compare this to this circuit, okay? And what you'll see is, in this circuit, when the output is high, there's no problem because you can close the switch and there is a path to VDD. But when the circuit has to go low, when Y has to go low, there isn't a clear path to ground. So what we have done is, for this switch, we have to put another complementary switch driven not by B but by B bar, B complement, and create a path to ground. So this is a rule. Every circuit node must always have a low resistance path either to VDD when it's going high or to ground when it's going low. So the proper output of the AND function when B is 0, right? When B is 0, a low, right, is 0 volts, right? So the proper output of the AND function of A and B is a 0, but that 0 only happens in this figure. So you need this extra switch is the rule. Okay, with that rule, let's talk about some actual circuits. First with NMOS, then with the CMOS transmission gate. So operation with NMOS transistors as switches. Implementing the switches in a PTL circuit with single NMOS transistors results in a simple circuit with small area and small node capacitances. These advantages, however, are obtained at the expense of serious shortcomings in both the static characteristics and the dynamic performance of the resulting circuits. So, while this switch seems like easy and simple, there are many disadvantages. So, as we try to understand what is going on here a little more, here's something to remember. Any MOS transistor is symmetric and its drain and source are interchangeable. What that means is, if you're given a device and you don't know, there's no rule that says one of them is the source and one of them is the drain. They are interchangeable, which is different from a BJT, right? With a BJT, generally an emitter and a collector are not interchangeable. But with MOS devices, they are interchangeable. And this interchangeability plays a big role as these switches are implemented. In fact, you can see in the drawing here, in one configuration, when V input is high and the gate is always at VDD, that's the enable signal. When the input is high, this terminal is operating as the drain and this is the source, and the output is coming off of the source. But when the opposite happens, when the input is low, what you find is this terminal is now the source and this terminal is the gate. Okay? All right. So, operation with NMOS transistors as switches. Here is the basic NMOS switch. It's implementing some kind of an AND function. The gate is always high. When the input goes high, you want the output to go high, right? Basically, that's a gate. And the gate is controlled by this enable signal. For the low, when the input is a low and the output and the enable says, okay, send it through, then whatever is here comes out as a low. Okay, actually, I probably missed. No, maybe it's later in the future. Sorry, I seem to have lost one slide. Okay, don't worry about it. I think I will, sorry for confusing you by going back and forth. Yeah, okay. So I've described to you when Vi is high and Vi is low. When Vi is high, and this is enabling it. So basically every time the gate enable goes high, whatever is on the input has to come to the output. That's one way to think about it, right? All right. So a capacitor is shown at the output, and the charging of the capacitor, as we know, happens slowly, right? There is a curve that it has to follow. Similarly, when the output has to go low, it falls in this way. And the halfway point where you reach VDD by 2, because VDD is the highest, actually it's VDD minus VT. The halfway point is defined as T. The time at which the halfway point is achieved is called TPLH, low to high. Similarly, falling wise, when it falls to 0, it's called TPHL, high to low. So in the switch, the source and drain keep interchanging the roles. The terminal that was previously the drain is now the source. The terminal with the higher voltage in an NMOS transistor is the drain. So anytime there is a high voltage here, for example, this goes high, this becomes the drain. Here, when the input is 0, the output can be high because the capacitor is holding a lot of charge. Hence, this takes on the role of the drain and this side becomes the source. And these are NMOS transistors, right? So this rule also is something to remember. The terminal with the higher voltage in an NMOS transistor is the drain. The opposite is true for the PMOS transistor. Okay. Now, a lot of analysis for this NMOS switch is given in the textbook, and I thought before we get too confused about how do you find overdrive voltage and TPL, I mean TPHL, TPLH and all that, I thought we should get ourselves memorized or familiarized again with these relationships for drain current and for saturation voltage and all that. So I brought this slide back from our chapter 5 notes 5.1.6. So I hope you remember the triode region, saturation region and all that. Here are the formulas we use for diode drain current in triode and drain current in saturation, and this curve. Okay, you'll find that this particular blue shaded formula is used a lot in analysis also. This is similar to this, but this form is more common in this chapter. All right. So operation with NMOS transistors as switches continuing. Let's focus on when the input is high. So assume that initially the output voltage V0, the output is 0 and the capacitor is fully discharged. When the input goes high, the transistor operates in the saturation mode since V drain to source is VDD, right? Drain to source, because this is ground almost, right? Because there's nothing there. So you can say that this is grounded, all of VDD appears across here. So VDS is VDD, and so it's in saturation. And it delivers a current ID to charge the capacitor, which is like this. In the gate source path, right, gate to source, VDD is VGS plus V0. That means VGS is VDD minus V0. So this VGS, if you substitute with VDD minus V0, you get this as the drain current for this situation. Now, one of the issues is that VT is not a constant, but it is determined by the body effect. We studied body effect briefly, I think last week or a couple of weeks ago, and we know that VT, which is not constant, follows this formula, and you know this phi and this gamma are new things that we are introduced to. But knowing VT, you can then solve for ID. Okay. Now, one of the things to realize is that the high output voltage VOH, which is what this reaches, is not equal to VDD, right? Ideally, we want it to be equal to VDD, but it's not. It is VDD minus VT. And VT can be as high as 1.5 volts. So if you have a 5 volt VDD and you take out 1.5, you may only reach 3.5. Which is one of the problems with the NMOS pass-through logic. Okay, let's move on to the next slide where we talk about when the input is low. Now the terminals are reversed. This becomes the source, this becomes the drain, because VO is at a higher voltage, its charge and C is being held. VI becomes lower, then current flows in this direction and it's still in saturation. So assume that initially VO equals VDD. The source is now at 0 volt here. The terminal that was previously the drain is now the source. At T equals 0 plus, the transistor conducts and operates in the saturation region. As C discharges, VO decreases and the transistor enters the triode region at V0 equals VDD minus VT. The capacitor discharge continues until C is fully discharged and V0 drops to 0. So this is the operation of the NMOS pass-through logic circuit. NMOS switch problems. So even though we can get away with one switch, it's not the best because the presence of capacitance C at the output node causes a delays in the rise of the output voltage, right? High output voltage VOH will not equal to VDD but will be VDD minus VT, and that's a problem. So in summary, the NMOS transistor transmits the the zero level to the output perfectly and thus produces a good zero. But for the high level, a lower value of VOH ends up creating a poor one. That means the one which ideally you want it to be VDD is not so great. So that's a problem with the NMOS pass-through logic switch. We have some problems, we'll come back to this later. One of the topics of interest is, we know that the output voltage high is only VOH, which is VDD minus VT. How do we get that back to VDD? So, is it possible? Yes, it is possible. But of course, nothing comes cheap. You have to put some cost into it. What is the cost here? If you stick a PMOS device, now this is our NMOS switch. It is connected, let's say in this case, to a regular CMOS inverter. So from the output of this inverter, if you put a feedback path like this shown, then you can achieve this. Your output here will go back to being as high as VDD and there is no drop. So that's one method, that's called the circuit-based method, where a PMOS transistor QR is used in the level restoring function, means you are restoring the level from VOH to VDD. The other method is using certain types of technology, these are called zero threshold devices, for which Tn is 0. So, VOH is VDD minus Tn, which is 0, so VOH and VDD are the same. So there's two methods to do it, and that is something you should be aware of. Alright, now we come back to the use of CMOS again as transmission gates. So we saw that NMOS is great, it's simple, it's cheap, but it has problems. So let's see what the benefits are with a pair of transistors. Great improvements in static and dynamic performance are obtained when the switches are implemented with CMOS transmission gates. NMOS transistor transmits the zero level to the output perfectly, the NMOS, and thus produces a good zero. PMOS does exactly the opposite, that is, it passes the VDD level perfectly and that produces a good one. So you notice that both NMOS and PMOS work together to get us both the 0 level and the 1 level to be just perfect. NMOS is good at pulling the output down to 0, while the PMOS is good at pulling the output up to VDD. These are also the roles they play in the standard CMOS inverter. We've seen this before. So, how do you explain the logic? Yeah, this is what I was looking for. The voltage at Y is equal to the voltage at X when we see, that means the voltage here is high, which is VDD. Y equals X if C equals 1. This is the logic way of explaining it. This is the voltage way of explaining it. All right. So again, we have the two scenarios to look at. The input being high for the transmission gate switch, and the input being low for the CMOS transmission gate switch. So both QN and QP work together in each scenario. Previously we had just one NMOS device that did the entire, trans switch function. Here we have both of them work together. So what you'll notice is, again, there is the interchangeability, right? The source and drain switching happens, no doubt, for both, for QN and for QP. But if you just look at when the input is high, the P channel will continue to conduct. One of the problems is that if you only have an NMOS device, at a certain point the conduction stops and you only reach VOH, right? But with both devices, the P channel will continue to conduct until C is fully charged, and VO is VO, which is the output here, is VO high, which is VDD. So it provides the gate with a good one. The same thing with the when you have to go low on the output, which the NMOS device used to do anyway. The N-channel device will continue to conduct until C is fully discharged and VO becomes VO low is 0. It provides the gate with a good 0. So both a good 1 and a good 0 are possible once you have a CMOS pair as in your transmission gate. Okay. All right. So there is an example here, which is actually exercise 14.4. Hold on. Yeah. There is one example 14.2 for just the NMOS, and then there is a exercise for this, and it's a complicated exercise. There's so many things to find. First of all, of course, the over VOH, what value do you reach? VOL, what value on the low side you reach? But then for the situation in figure A, find all these currents, IDN, IDP at t equals 0, then IDN, IDP when t equals, the point where you reach VDD by 2, which is TP low to high, TP low to high. Similarly, for the figure B, you have to find IDN, IDP, and then IDN at the time high to low, because this is discharging, and then find TP. So all these things to find, you need a lot of formulas, and I thought I would capture all the necessary formulas both for the upper portion going high and the lower portion going low. So you have the time formula, right? What is TPLH and what is TPHL? When does that happen? So that's one formula. Then all these currents, you need this IC average. To find this IC average, you need so many things. So I've given you all those. You'll see that the formula for current is basically the same that we studied earlier in chapter 5 and all that for the drain current of a device, both the P type and the N type, right? So this formula, either each of the devices is in triode or it's in saturation mode, right? So you need those formulas. Then you have this for VTN, so the body effect formula. Similarly, for the P type, you have the body effect formula. Then you have for the discharge situation, where your capacitor is discharging to give you a 0 at the output, a low. Then you have to deal with the P-type transistor. So here are the formulas for the p-type transistor. So I've given you all these formulas, I've tried to summarize them, and you'll see how we can use them when we actually do some problems. So that was the introduction to the CMOS transmission gate and the NMOS gate in pass-through logic switching. So one other important concept is called the equivalent resistance of the transmission gate. So we have a transmission gate, but we need to know if there is any resistance at all in the circuit. And obviously, even though these are nice smooth switching devices with low resistance, there is still a definite resistance. So we need an estimate of that. So this equivalent resistance of the transmission gate RTG is Rn for the n-type device in parallel with Rp equivalent for the p-type device. And for Q1, the n-type device in saturation, there is a formula. Qp in saturation, there is a formula like this. So you have to do this, then you have to find RTG. Sounds complicated. Luckily, there is a simpler formula which is called an empirical equation for the resistance of the transmission gate, and most of our problems will be using this. Now, once we know that this is a resistance and it's connected to a capacitance, you have like an RC circuit, right? And so finding TPLH or finding TP, the TP point when you're going low to high or you're going high to low, you can use this. Generally, they talk about low to high. For a step input, this is the formula. For a ramp input, this is the formula. Okay. Now, some more formulas related to this same TPHL, TPLH. So for a regular inverter, we know, this is how we model it. When this is going high for a switch, you can replace it with a Rn for the NMOS and Rp for the PMOS when it's going low, right? So this was for the inverter stage. So sometimes in these problems, they ask you to take the switch stage and the next inverter stage and do the analysis together to find, the uh, time for TPHL and TPLH. So that's why I've repeated most of these formulas again. So there's an Rn and an Rp, and for the Rp it's slightly different, and we have seen this before, these formulas, but I kind of brought them back so that you'll notice that in the next two slides where we talk more about time, because of the fact that this has a resistance and then there's capacitances in the circuit, is a complicated formula to find the TP, the average propagation delay, TP. So this circuit shows it consists of a transmission gate in the middle. It connects the output of one inverter to the input of the next. So it's acting as a switch. To find the total propagation delay, you can convert this into this simpler model with the gate, the transmission gate in the middle consisting of this, and this only RP and C out 1, and this the C in 2, right? So with this model, you can get the formula for TP to be like this, where there's an R1 here, but the R1 is just RP1, which is the P, resistance for the PMOS. So this formula, and then there's another general formula if you have a number of RCs like this, 3-section RC ladder network. So all these formulas are useful in helping us study the propagation delay, because Obviously, you are very concerned about speed, right, in a integrated circuit. As we are switching at high frequencies, all these tricks that you're doing to create new circuits, you're definitely worried about power consumption, and you're worried about time of transmission or propagation. So for all this, we have problems that we'll work through on understanding the TPs. Okay. All right. So we'll come back and do some problems. Let's continue with a bit of the theory again. So now that we have talked about pass transistor logic, PTL, can we implement some simple logic, not only just as switches, but also, some of these circuits, some of these logic relationships? And the answer is yeah. So here you can see we are doing a 2-to-1 multiplexer, right? So there's two inputs and we want one to come out based on whatever C the enable says. So that's what is achieved here. It means Y is C into A plus C bar into B. So either A or B will be sent out based on C. Similarly, this is a simple XOR, right? Exclusive OR. Either A or B has to be high for the output to be high. If both of them are low, then the output is low. If both of them are high, then the output is also low. So you know the exclusive OR, and that can be done using a transmission gate. Here's another interesting one. This is called complementary pass-through logic. So you have two inputs and you also have the complements of both inputs. So 1, 2, 3, 4. So A bar, B bar are both available. And then you also use them here. So you get Y equals AB, an AND function, but you also get Y equals AB bar, a NAND function, right? Both are available. So an example of a pass transistor logic gate utilizing both the input variables and their complements. So this is also possible using transmission gates. Okay. All right. Here's an example where we'll do a little more on the transmission gate. Then we come to the next topic and the last one, dynamic MOS logic. So far we have studied 14.2, which was pass-through logic. Another little technique that is used a lot is dynamic MOS logic. So far what we have studied, you can call them static circuits, and what we will see here in this section is dynamic logic circuits. So what's the big difference? All right. In a static circuit, you have a pull-down network, you have a pull-up network. So if you want to implement something like this, you have the pull-down, you have the pull-up. With dynamic, you don't need a PUN at all. You don't need the pull-up network. So this is similar to that pseudo NMOS we studied right at the beginning, right? So all you need though, you need two other things though. You need another transistor called a QP, and you need a clock. So this phi is a clock input. So you need a QP and another transistor called QE. If you have this, then you can just work with the PDN and get rid of the PUN totally and still be able to achieve this. Okay? But to be able to do this dynamic MOS, there are some ideas and concepts that you have to understand, and also understand the importance of the role of the clock. So the clock can be low or the clock can be high. When the clock is low, QP is turned off, QP is on, QE is off, and the circuit is in the setup or pre-charge phase. So when the clock is low, this is what you're looking at. When the clock is high, QP goes off, but QE turns on, and the circuit is in this phase. Okay, so the clock is important, and it creates two conditions called the pre-charge and the evaluate. So the pre-charge phase, QP is turned on and CL is charged. So this output capacitor is charged to VDD so that the output is a high. In the evaluation phase, QP is off, right? This goes off, and QE turns on. So now what comes here, or what, remember this is already high. Will it stay high or will it go low depends on the logic inside the PDN. If the PDN says, yeah, give me a low, then this will discharge because this is on. If the PDN says, no, no, stay at a high, because that's what my condition, my logic says, then nothing happens and Y retains this output voltage. So this is the basic logic of this dynamic MOS, and I will continue the theory and then do some problems in the next recording.